Okay. Hello, everyone. I'm Harry. So today we will learn motion planning together. If you plan to go to Peter's office hour today, I think the office hour will still happen. So you can just go to Peter's office in the regular time. Yeah. So let's start. What's motion planning? The problem can be formulated easily. So given some start state xs and goal state xg, what do we need? We need a sequence of control inputs that leads from start to goal. And this is very intuitive, but actually solving this problem is very, very tricky. There are 2 points I can think of. One is we need to avoid obstacles, and later we will show like avoiding obstacles can be non-convex. Another point is for systems with under-actuated dynamics, it's tricky because we cannot simply move along any coordinate at will. Like most of the dynamic system is under-actuated dynamics, like cars, helicopters, airplanes, and so on. So we will check a few examples. So this is helicopter, path planning, carpal swing up, and acrobot. If we look at them carefully, we will find they are constrained by some joint limits or some other constraints. So they are under-actuated systems. And also there are some more realistic example, like in the industrial world, there are these things like ensembling a car. It can be another kind of motion planning problem we want to solve. And more examples. On the left is a few agents want to move the piano out of a very constrained room. And on the right, we can see one bipedal working agent and object manipulating robot. So these are all lying in the umbrella of motion planning, or we can solve this by this method. And there is a sequence of image. On the top row is a simulation figure. In the simulation, we want the robot to grasp or get the object under the table, and the lower row is the actual robot can follow the trajectory in the simulation and achieve the goal we want. So today, this is an outline of today's lecture. Firstly, we will learn about configuration space, which is the basic or the configuration space is the starting point we want to learn motion planning. And also, we will learn optimization-based motion planning and sampling-based motion planning. And we will learn the difference between these two. So starting from configuration space. So some of you might have known, but some might not. This is a concept figure of configuration space. On the left is a robot arm, and on the right is its configuration space. The darker area is the constraint area, and the white area is the feasible or free space that the robot arm can move. So what is configuration space or C space? it is a set. X is the pose of the robot. So instead of in the 3D space, we think of this problem in another space, that is the pose of the robot. So there are two examples. The workspace on the left is we want to move the little rectangle in this space, and the black triangle is the obstacle. And on the right is the configuration space. We can see there are another layer of blue obstacles that is due to the collision between the blue rectangle and the triangle. So that's the configuration space. And on the lower row, we can see similar effect. Like we want to move the circle, which is another rigid body. And on the right, there is another blue layer that is caused by the collision. So this is the difference between workspace and the configuration space. So now we want to go into the optimization-based motion planning. Leading motion planning methods based on RRT and A* slow down a lot as the dimensionality of the state space increase. So fast planning is very, very essential for solving problems. And this starts from some reactive control, that is potential-based method. If you are interested in this, you can check this kind of ancient paper or seminal work. There are some optimization-based methods that optimize over the entire trajectory of starting from elastic bands and tromp and its variants like stomp and etomp or itomp. But here we find that in a few benchmarks, Trajopt, which is brought here by John Schumann, outperform most of other baselines, and we will learn that. Yes, so it outperforms other baselines in both shortest path length and also the computation time and also the success rate. So let's look into detail how to can we solve this by nonlinear optimization for control. So in the upper part, we can see one formulation, like xt is the state at the time step, at the final time step t, and xg is our goal. So with a few constraints, subject to xt plus 1 equals to f xt ut, and ut in set of u, and xt in set of x, and x0 is at the starting point. And can we reformulate this into another formulation? On the lower part, we see that we can actually just minimize u, but if we look carefully, we find there is another constraint that is xt equals to xg. That means we want the ultimate state to be equal to the goal state. And because this hard constraint, so this usually requires using some infeasible method, like learned in previous lectures. We will write something in the whiteboard. Sorry. Oops. Oops. So we want to minimize theta 1 to t sum over t of theta t plus 1 minus theta t squared plus some other costs. So this is our main objective, and subject to theta 0 is the start state. Theta t in the goal set, sorry. And there are some more limits, such as joint limits. Like if you are using a robot arm, there are some joint limits you want to follow. And also something important for all robot parts. No collision. So this is another constraint. Like if you are using a robot arm or any kind of robot, you don't want collision. As previously mentioned, this part can be non-convex. So we cannot simply do a convex optimization and solve this. The solution we use here to solve this is called sequential convex optimization. Sequential convex optimization is some kind of method that repeatedly approximate the non-convex problem with a convex problem and solve the approximation step by step. So looking into detail of this constraint, like for all robot parts, there is no collision. We can define what is collision, and here we want to draw something here. So there is a body A, body B. This is some point at PA, PB. So if PB is outside A, then this distance is positive, and we call it sign distance, which is greater than 0. And this is pretty intuitive. If this PB is inside A, we call this sign distance is smaller than 0. Mm-hmm.
What did P and PB represent, or what do the squares represent?
Oh, these are two bodies, like two rigid body. Yeah, and yeah. We can write this in a more strict way. The sign distance A to B of theta is approximately equal to n PB minus PA theta. So this is saying this is n is the vector, the normal vector, and this is the distance between these two. So this decides the direction and or the sign. We can also rewrite this in another way. SD AB theta 0 minus N T J PA theta 0. Sorry, it's a bit. Can you still see this? Times theta minus theta 0. So this is a different formulation. Like this is the original distance, and the latter part is the distance moved from zero to from theta 0 to theta, and the J is sort of dynamics or a dynamics model or yeah. And so now we have now we know what is sign distance. We can add this as a penalty in our optimization problem because we want the sign distance to be positive so that there is no collision. So can I erase this part?
Yeah. Question.
Mm-hmm.
Can you explain the PB and PA theta a
P.
little bit? So why there's a theta argument in PA?
Oh, so PB is you can imagine PB is a fixed body, and the PA's position is depend on theta. Theta is the configuration of A. Yeah. So I'll erase this part. Oh, I think J is the dynamics. Like from this configuration, change to this configuration. So what should they change in the workspace? So J is the function to do that. Yeah. And so what kind of penalty we can add? We can do something like this. So we have 0 sign distance here, and here we call it safe distance. And so in the 0 point, we have this square and this rectangle that has 0 signed distance. And at this safe distance point, we have this square and this rectangle has a positive safe distance between these two. Yeah, and like to the left, we have these two overlap, which is collision, and we want to penalize this, so we have a higher value for penalization. And on the right, we have like very far away bodies, and as long as it's the sign distance is larger than the safe distance, we don't penalize. So this is a hinge loss, or the hinge loss like penalization we want to use for this optimization problem. Yeah. Okay. Okay. So now we want to consider another thing that is continuous time safety. So what is continuous time safety? So if you are controlling a robot arm, so there is a volume between time steps an arm can sweep out. So the whole volume of the swept out, you don't want any collision. So if you just check collision at every time step, then there are still some collision in between time steps. So you can always reduce the time step, but it's kind of hard. So we consider just check the volume and the other bodies and check collision between those two. So this is actually very fast overall because you can allow a costly sampling trajectory. That means you don't check every consecutive time step. Instead, you can check like a few steps away and just roughly estimate the swept out volume. So this makes the collision check even faster. And also, actually, this method confines better local optima because you check the volume instead of like time step points. So this is another thing. Now we will see some example. So this is the collision-free path for Dubin's car. It starts with collision with some body, and after the optimization we just derived, it finds the path so that there is no collision, and it's a feasible path.
Can you explain the figure in the previous slide?
This one?
Yeah.
Okay.
Explain how the figure represents.
Oh, okay. So AT is like the robot arm at time step t, and the AT plus 1 is the robot arm at time t plus 1, and the shaded area is the volume the robot arm swept out, and the B is some obstacle you want to avoid. So although AT and AT plus 1 are not did not collide with B, but the volume actually collide with B. So what you want to check is the volume does not collide with B instead of just single time step collision.
But why do you say that it does not collide with B? It doesn't like B clearly go into A if A were to move along that path?
Yeah. So if everything is discretized, so you only check AT and AT plus 1 exactly, but here we want to consider the time in between AT and AT plus 1. Yeah.
Question.
Mm-hmm.
Here you're assuming from AT to AT plus 1, the movement is just purely linear. What if it's not linear?
Yeah, it can be nonlinear, but like if the time step, the gap between two time steps is very small, it's very reasonable to approximate with a linear function. But you can always like adversarially invent something that is nonlinear. Then you can cut the time step even smaller, I think, still with a linear function, or you can invent some new algorithm to check collision, because I think collision checking is not only for like linear shape. Yeah.
What do you mean by allows coarsely sampling the trajectory?
Oh, coarsely sampling trajectory means you can actually check the swept out volume from AT to AT plus 5 maybe, if it's just some linear motion. So instead of checking AT and AT plus 1, AT plus 1 and AT plus 2, like step by step, you can just roughly estimate like from AT to AT plus 5. And although it's not exactly the same volume, but it's similar, so and if it's linear, then it's the same. So it's much faster, yes. Yeah. Okay. Some more example. So this is industrial box picking application. So you can see the consecutive path is the planning trajectory, and the robot arm actually follow the planning trajectory and pick the box successfully. Yeah, maybe we can skip this because it just repeatedly do this. Yeah, there is another DRC robot using planning to go inside the door without collide with this obstacle. That's not the most intuitive way to avoid this obstacle, but that's the algorithm. Yeah, and touch the button. Okay, so now we have some algorithms. We need to benchmark everything. So there are two benchmark. The first one is you just control one arm, that is 7 degrees of freedom, and there are 198 problems. And the harder one is 18 degrees of freedom with 2 arms plus base plus torso, and there are 96 problems. And here is the benchmark results. We find that Trajopt which is much faster than, like if we check time, it's faster than sampling-based method like bidirectional RRT and Tromp. And if check the success rate is higher and the path length is shorter. So in this kind of problem, Trajopt is good. It is better than the other two. One more example. So first, we represent the lab environment into a obstacle space. So we want to do reach and grab.
I have a question.
Mm-hmm.
How do you determine how far away your discretized points are?
Sorry, can you say that again?
How do you determine how far away your discretized points are?
Oh, I see. So usually this is, if you are doing this in a simulator, usually you cannot decide this, although you can always hack the simulator. I think, so usually as long as the time gap is very small, then it's fine. But how do we define small? That's another question. I would say smaller time gap will make your algorithm very inefficient, because the trajectory horizon will be very, very long if the time step is very small. But if it's very large, then the gap is too large, so we miss something in the middle. So it depends on your problem, but also depends on the efficiency you want. Yeah, so the trade-off between like knowing everything and like efficiently solve this. let's continue to this video. Yeah, this is in the simulator planning. Like the robot arm is planned to grab something, reach and grab something. Very fancy. Yeah. And it's the actual PR2 doing the same thing and succeed. And then we want to do throwaway. You can see like this throwaway, we need to avoid some obstacle, right? So and after some optimization, the robot find a path. There is no collision, and there it is. And it's very exciting, so other students also want to watch, and we gave them some mosaic. It's so slow. Oh, come on. Yeah, I think that's it. I think everyone in the classroom can do faster than this, but yeah, that's the algorithm. And if you think it's too slow, you can like invent some new algorithm to like surpass this. Yeah, and one more application, that's the steerable needle. So if you are interested in some medical application, or if you are familiar with this, sometimes we need some needle to be inside some tissue, and even we want the needle to navigate around some sensitive structures in human. Although it's a simulation, but we can see it's very sensitive. So some introduction to the needle. It has a bevel tip. It's highly flexible, and it's in the SE3 space, which is R3 times SO3. And R3 is the XYZ, like the 3D space, and SO3 is the 3D rotation space. And there is one more constraint, that is it should always follow a constant curvature path. So let's formulate this. So here the yellow part, the O is some obstacle, and we find that we want to minimize three costs. One is the cost delta, one is cost phi and cost phi, and another is cost O. So they are the translation cost, the rotation cost, and the obstacle cost respectively. And if you check the constraint, subject to the first line might be a little bit tricky, but you can think of this as so the same as xt plus 1 equal to f xt ut. So the exp wt is something like rotation motion, and the exponential to vt is the translation motion. And here we want to say, starting from xt, we do the rotation and do the translation, we can get xt plus 1. So I think they use some group theory representation instead of regular representation, but the intuition is simple. And also there is another constraint, that is sign distance between state and the obstacle should be larger than the safe distance plus the needle's distance, like some certain boundary we cannot break into. And x0 is belong to the entry set, and the xt belongs to the target set. Phi t is the rotation degree, and it should be smaller than pi and larger than pi, smaller or equal than pi and larger or equal than negative pi. And here kt is the curvature. So we said we should always follow the constant curvature. So here kt is always kmax.
Why the first line equals to 0?
Why the first line? Oh, because there is an inner product. So if you write it, if you give exponential to both sides, you will have xt exp wt exp vt times xt is e to the 0, 6 dimension 0. And yeah, so that means xt do the motion of rotation and do the motion of translation and take an inverse times the future xt plus 1 should be 1, right? So because e to the 0 is 1. And then if the inverse of a and b times together is 1, then they should be the same. Yeah, that's why we have a 0 on the right side, because there is a log on the left side. Yeah, but it's just rough description. If you want to know the detail, you can take like Lie algebra or something. So here is some result. If we perturb the alpha, the coefficient for the obstacle loss, the obstacle objective, we find when alpha O is 1, the distance is small, and when alpha O is 10, the distance is large. You can see that little needle and the obstacle on the left, right? And here is some result. We find optimization-based method can be fast and can have better success rate, I would say. And so why is minimizing twist important? I think this is very intuitive, like because the needle is inside the human body, so you don't want the needle to twist in the body and if you rotate, you will check the fake human tissue, and it will hurt a lot of things. Yeah, and if we expand this to channel layout, which is usually called brachytherapy implants in medical area. So we want a channel of tube or the needles, and we want to guide them to some target tumor area. And the cost function, the objective and the constraint are similar, but there is one more thing. We relax the constant curvature. The previously kt is equal to kmax, right? So here kt is smaller than kmax, larger than k0, and we have one more constraint, that is the delta sum over kt is smaller than cmax for the channel planning. So because previously it's one needle and here is a channel. Yeah, so here are some results on channel layout. Yeah. So optimization-based method, if you are interested in this, you can try it yourself on with the code from rll.berkeley.edu/Trajopt, and there are a few benchmarks you can try out. And if you find new things, please tell us. Yes. So some more video. Yes. So it's robot navigation planning. So this is the optimization and find trajectory without any collision. Following the trajectory. Okay. Okay, he made it. Yes, so this is more things. And yeah, so after optimization-based motion planning, we also want to look at some sampling-based motion planning. So I think inside of this section, we want to learn PRM, which is Probabilistic Roadmap, rapidly, and the RRT, rapidly exploring random trees, and smoothing, because the trajectory you find with this method can be like very noisy, and you want to smooth them out. And I think we can take a break after PRM because PRM is really, fairly simple. So so probabilistic roadmap, we have a space Rn that is the rectangle, and we have some forbidden space that is the dark yellow area, and we have some free and feasible space that is the light yellow area. And the configurations are sampled by picking coordinates at random. So we randomly select one point in this space, and we repeatedly do this or in parallel. Like we sample a lot of points, and we find some of the points are feasible, some of them are not. So we find the collision-free configurations as milestones. So they are marked pink. These are our milestones. So each milestone is linked by a straight path to its nearest neighbors. It's linked to, like, you can choose the hyperparameter k, like 5 or 10. You find the 10 nearest neighbor and connect them with some path. And then we remove the path that there is a collision in the middle. And we do this for all the points we have, and now we have a graph. So if we want to start from the starting state S and we want to reach the goal G, we just do a search with some computer science algorithm. Yeah, and this is this is a very, very simple algorithm, but very useful. So here is some description: initialize set of points with xs and xg, and then we randomly sample points in configuration space, and then connect nearby points if they can be reached from each other. So previously we just removed the lines that is blocked by some constraint. Sometimes if in the real world you can always do some optimization to find if 2 points can be reached or not. But in this example case, we just say if there is some collision, then it can never be reached. And then we find the path from xs to xg in the graph. Yeah. So so alternatively, keep track of connected components. So this is a better algorithm. So you keep track of connected components so that you don't need to do the final search, or you can prune the final search to a smaller space. So more example. Oh, I think this cannot be played. I don't know why, but we can see the other example, which is more interesting. So this is a robot trying to climb. Yeah, so this setting is very friendly to PRM because it's just like there is a space and you sample a few points, and if that point is close to the physical point that you can put your foot on, then it's okay. So I think this task is very particularly friendly to the PRM method. Yeah. So sampling. So how do we do sampling? We can sample uniform from 0 to 1, like for each coordinate. This is one thing, and we can how to sample uniformly at random from the surface of the ND unit sphere. So we can sample from ND Gaussian, and because it's isotropic, that means the identity is the covariance matrix is at identity. Then we can just normalize because for every direction is the same. So there is another question for you to think after class. So how to sample uniformly at random for orientations in 3D? Yeah. PRM challenges. When connecting neighboring points, only easy for holonomic system. That means for which you can move you can move freely at will. Like whenever you want to reach from this point to the other, you can do that without any constraint like joint limits or something. And generally requires solving a boundary value problem. So this is similar to our previous optimization problem. So if previously we say from 2 points, if there is some collision, we just ignore that line. And here we say if there is some collision, actually we can do some optimization and find if it's reachable or not. Yeah. And collision checking often takes majority of time in application. So with PRM, you need to check collision between every line, between every pair. So there are a lot of lines that is useless, but we still need to check collision for every of them. Yes. So here are some pros and cons for PRM. The pro is it's probabilistically complete. That means with probability 1, if it runs forever, it will contain a solution path if there is a solution path. And the cons is obvious. The cons are obvious. It requires to solve 2-point boundary value problem, and also it need to build graph over the entire state space, which might be very expensive. Yeah. So yeah, let's take a 10-minute or 5 minutes break, maybe 10 minutes break, and we will go into RRT. Yeah. Hi.
How are these equivalent, or did you say they were? Because like
Yes.
this one, it looks like this one doesn't care about the magnitude of the U's at all, so
Yeah.
they're not equivalent.
I think so. This is trying to minimize the target, the final location, the final state, and the target state, and this is trying to minimize the control, but with the constraint that the target and the goal should be the same. So I think they are at least surrogate, maybe not like strictly equivalent, but if you check yes, this thing, here we actually minimize the path length, like because theta is the degree of freedom of the index configuration space. So minimize the control sometimes is minimize the path length, but it's not exactly the same, I think. Yeah.
Okay.
Yeah.
But this one does not minimize the path length. It's only
Right.
checks
It is.
for the last. Okay.
Yes.
And then can you explain again why this may require using an infeasible method?
Yes, because sometimes xt cannot be equal to xg.
Okay.
So sometimes you have to reach some infeasible area. So that's infeasible.
All right.
Yeah. Mm-hmm.
And then how did this formulation relate to like, are these two just like not used?
Right. It's not used. Like the one we use is this one.
This one.
Yes. So other costs can be like some smoothness or some constant speed limit you want to add. Yeah.
And then is joint limit just like what you mentioned earlier about how like some
Like
only in the configuration?
Yeah, in the configuration space. Maybe the next page is. Oh, sorry. Where's the configuration space?
Oh, configuration. This.
Yeah, this one. Like the limit is like this shady area. Yeah, because it's limited by the mechanical like problem of a robot arm or something.
Okay.
Yeah. Mm-hmm. Hi.
I have a question. So in the previous 2 lectures, we learned about optimization-based control. And then how is it different from motion planning? Because here, my understanding is that we again formulate this based on like an optimization problem, and then we use again the shooting or collocation methods.
Yes. Yes.
Right?
Yes.
Is that what we are doing here again?
Yes,
using
I
the
thi-
same methods as we.
I think it's very similar to previous one, but Motion planning is a specific line of like a problem, so.
The difference is like what between motion planning. What is the difference between like motion planning and optimization based? Optimization based motion planning or optimization based control?
I think, well, optimization based things are very similar, so there is not much difference, but the sampling base, like the sampling base is very different from that. Yeah. So.
But for the optimization part, for the first part, Trajopt and stuff. So what are the methods that we use after we formulated in the optimization for?
So we formulate a non-convex optimization problem, and then we, for like every short time step, like we linearize them and make them convex optimization. And as long as it's convex optimization, we can use like optimization solver to solve this.
Like gradient based and stuff.
Yes, or gradient based or just two order method, second order method. Yeah.
That's what you mean by like sequential convex optimization?
Yes. You iteratively approximate this non-convex one by a sequence of convex ones.
But the point is, like, if we optimize for a short time and then go to the next time, then is it going to be like optimal control? Because like it's not going to be necessarily the best path, like generally in total.
Yes.
You know what I mean? Like maybe this action is the best for now, but if you take the other action, which is not as good, but later on you will have a better situation.
I see.
So there's like horizons and stuff, right? Where you plan over.
Yeah. So the point is like maybe the action, some action is not optimized now, but later on you will get a huge benefit from that.
I see. So there is another kind of method you can, if the obstacle is some non-convex shape, so you can always linearize them with a convex thing. Like that's something I can think of.
But for the optimization-based motion planning, you just do it like for like a small time step and then go to the next and go to the next, right?
Yeah.
At each optimization, you don't consider what happens later on, right? Is it the case or not?
Yes. So you're saying that might be suboptimal.
Yeah. Because like the point is for optimization-based control that we have is that like all the sequences were like included in the cost. So the cost was like from the first step and the next step all the way to the end.
Okay. Yeah. Maybe I can get back to you like later. I'm not sure about it. Yeah.
That's kind of.
What's your name? Mehdi. Okay. Can you send me an email to remind me?
Sure.
Okay. Thank you.
What is n hat in that equation? What is n hat in that equation?
Oh, and is the normal vector, like indicate the direction.
The normal
Yeah.
motion?
Yeah.
Okay.
Yeah. Okay. So I hope everyone's here. So let's start with some more sampling-based motion planning method, which is RRT. The basic ideas of RRT is very intuitive. So we build up a tree through generating next states in the tree by executing random controls, and but it's not exactly above to ensure good coverage. So we will go over RRT on the whiteboard so that we can. So we are doing RRT. So there's a function called generate RRT with some initial state x, some k for iteration, and some delta t for time. So there is a tree that is initialized with one node, x init. And we do a for loop for k equals to 1 to k. We want to do x rand. So random. So we first sample some random state from a random state generator, and we find x near with nearest neighbor. So we find the nearest neighbor of the generated x rand in the tree. Okay, and then we select input x near u delta, x near x rand, x rand, x near. So we have some randomly sampled point x rand, and we find its nearest neighbor inside of this tree, and this is trying to find some control that can go from x near to x rand. So this select input is doing this. And then we actually perform this u, we just find new state. X near u delta t. And now we have a new point. We put it in the tree. T add vertex x new. And we want to also add the edge. Add edge x near to x new u, and then we return the tree. So so let's go. Oh, sorry, this is random. So we go over this. Like we have some initial point x init, and then we sample some x random here, and we find this is in the tree, right? Because we initialize the tree with this, and then we find the nearest neighbor to this, right? Because there is only one point, and it is its nearest neighbor, and we find how can we achieve this x rand from this x near. Then we find, oh, there might be some u that can achieve this line. And then we actually perform this u starting from x near, and we find, oh, actually it almost reached the x rand, but it doesn't reach x rand because it stops at x new. And this is the point that we can achieve actually. And then we add this x new to our tree and connect this edge. This is RRT. Is this clear?
For the nearest neighbor, so which point you are selecting as a reference?
So for nearest neighbor, you select the nearest neighbor of x rand from this tree, from this T, yeah.
Okay, but there might be a lot of points in the tree already.
Yeah. So you find the nearest one in this tree, the nearest one to this.
Okay.
Yeah.
So the x rand is just one point.
Yes. please.
Okay, I'm a little confused why xrand and xnew are not the same one. Is it because model mismatch or like what's going on?
Yes, so this is like you have two states here, and you can infer the U, like what kind of action or control you want to perform. But when you actually perform this control, the inverse model like thing is slightly different, different from the real world control, and so it only reach x new instead of x rand. That's my understanding.
Are you saying that to do RRT you need to like try actions in the real dynamics? Try actions.
Oh, so if it's just points and you just if it's just simple points, you can just use you can always reach x rand with some control u, but if it's a real robot, the sampled point might not reachable. So although you inferred u, but when you perform u, it does not reach x rand actually.
Would you have to perform U on the real robot?
In the simulator, yeah, in a in a forward model, yeah.
Also, when you are generating the xrand trees, do you generate by propagating your dynamics model forward, or do you actually just randomly sample in the space?
So for x rand, you just sample, you just randomly sample, and for x new, you need to forward.
Okay, so there's no guarantee that xrand is within your reachables.
Right. Yes, because it's just sample. Yeah. Yeah.
Then how you find that U? So how you solve for that equals?
Like you can always solve this with an inverse dynamics model, like
If it's not reachable, like how
approximation, I would say. Yeah. So, yeah. So if we check the small words below, there are some more things, like the random state generation generates the goal with 1% probability. So we don't want it to miss the goal, and also the select input, often a few inputs are sampled, so they just use sample like to get this. But in harder case, you can always learn a inverse dynamics model to do that. Yeah. So when you select random point and expand nearest vertex towards it, you can always bias samples toward largest Voronoi region. And Voronoi region is some algorithm that compute the area for shortest distance, I think. Yeah, I'm not 100% sure about this, so maybe you need to like check it online. Yeah. So there is a visualization of RRT. So it starts from the middle and expand the tree with this algorithm, and we can see it expand pretty fast, and yeah, finally reach the last figure.
What's the red on the bottom?
Hmm?
What's the difference between the top and the bottom?
Oh, the bottom is actually the Voronoi region. The red line actually divides the space into Voronoi region. Yeah, and the black line is the lines we have in the tree. Yes. Yes, and here are some RRT practicalities. Nearest neighbor need to find the nearest neighbor efficiently. KD trees data structure can find this, and you can also do locality sensitive hashing. There are some more algorithms you can find for finding nearest neighbors. Also, select input. So you can it's another two-point boundary value. Two-point boundary value problem that can be solved with optimization, like previous slide, like in PRM, right? So yeah. And RRT extension, when there is no obstacle, that is holonomic, we can do something like this. And with obstacles, and it's also holonomic, we can sample, and until we reach some collision, we stop, right? Like that's why we always have a x new instead of x rand, because there might be some obstacles. And for non-holonomic case, so you can approximate solve 2-point boundary value problem, but it's not guaranteed. Yes, is this a video? No. Yes, so this is another picture of growing RRTs. So with RRT in our hand, we can do bidirectional RRT. So suppose we want to start from XS to XG on the left. We expand the tree toward different direction, and until the circle touch XG, we find the goal XG. And on the right side, we find something new that is bidirectional RRT. It starts from both the goal and the starting point, both the starting point and the goal, and expand together. So when the RRT trees reach each other, then we already find the path from the starting point to the goal. So what's the benefit of doing this? The expansion volume is the trick. Like on the left, the expansion volume is very large, and on the right is smaller, like two small circles. The area is much smaller than the left side. Yeah. And extending this, we can have multi-directional RRT. So we can always start from other starting point and expand the RRT instead of starting from the starting position. And this is particularly useful when there are some trajectory that is hard to explore from one direction, but it's very easy. It's very easy for RRT from other direction, like this case. So I think the top right figure show that the blue one can hardly explore RRT, can hardly explore the trajectory, but the red one from outside can easily go into that narrow trajectory. Yeah, so this is the case when you want to use multi-directional RRT.
Sorry, can you explain the configuration there?
Sorry.
So we see that heart shape, right? So does it mean it's a boundary that you cannot go out?
Yes. So the boundary is some rigid body you cannot, or that can cause collision if you want to go out. So whenever you sample a point that is out of the boundary, then you will be blocked by that boundary. So your x new will still be inside of that boundary. And so in that case, it's very hard for the inside one to go outside, but the outside direction can easily go inside because because of the shape of the boundary. Yes. So there is another variant of RRT that is resolution complete RRT, like RC-RRT. So the issue with RRT is nearest points chosen for expansion are too often the ones stuck behind an obstacle. This is actually showed in this figure, right? Like if you want to expand some blue trajectory, it will always stuck by the boundary. So how do we deal with this? We invent the RC-RRT. So we can go through this algorithm step by step. Choose a maximum number of times m you are willing to try to expand each node. And for each node in this tree, keep track of its constraint violation frequency. And okay, so what is constraint violation frequency? That is the frequency that the sampled point is out of the boundary. So that's the constraint violation frequency. And then we initialize the CVF constraint violation frequency to 0 when node is added to the tree. So initialize with 0. And whenever an expansion from the node is unsuccessful, like from one point you want to expand and there is some collision between the expansion, then it's unsuccessful, and then we increase the CVF by 1. And we increase the CVF of its parents node by 1 over m, and the grandparent by 1 over m squared, and so on. Mm-hmm.
What do you mean by like expanding each node? Because I thought in the RRT algorithm you expand the tree by just like picking a random point and then finding its nearest neighbor. So here it's like it seems a bit different.
Oh yeah, so when you have a sample, when you sample a point, and like you find the nearest neighbor is some point already in the tree, so you are expanding that point in the tree.
Oh, okay.
Yeah. So this is, and we need to check the last step. When a node is selected for expansion, skip over it with probability CVF over m. So, yes?
So when you skip it, does that mean that you go to the next nearest neighbor then?
Yes. So you need to choose the nearest neighbor, and then like in this algorithm, we do it with 100% probability. And in this algorithm, when we choose the nearest neighbor and we see, oh, you've been rejected for a few times, or you failed a few times, so we just give it 80% probability to still expand this node, and with 20% probability, we choose the second nearest neighbor. Yeah, so this is RRT, and when it's black, it's time to write something on whiteboard. Yeah, so here we want to do something called RRT star. So in this RRT, it's very simple, but it can be improved. So if you know A star, so RRT star has a similar intuition as A star. So you keep a cost function of different nodes, and if the nodes like if you find a shorter path with a lower cost, then you change the path, and so that your tree can find shorter paths than regular RRT. And yeah, it's a lot, so I'll start writing. So we have some vertex set V, start with X init. Is it too small? Okay. V X init. And we have some edge set that is empty. And then we do a for loop for I1 and 2. Still, we sample xrand from a function sample free. So the algorithm's functions changed slightly because it's from different paper, but it's similar as the previous random function. And there might be some new functions, so I need to explain that as well. So we also find nearest neighbor. Nearest G V E xrand. So this is getting the nearest neighbor of xrand in the graph with vertex set V and the edge set E. And then we steer x nearest x rand. So this is similar to the select input, you want to start from x nearest to go to x rand, but actually you cannot reach x rand because there are some certain limits, so you just go to x new. And we want to check if it's obstacle free between x nearest to x new. Then we want to do x near is near G equal to VE x new min gamma RRT star, that is a coefficient, or log cardinality V over card V to the 1 over D, and eta. So this is a new function near. That is, so previously we have some point here, and we sample x rand, and we find its nearest neighbor, x nearest, here, and we connect them. We find with the steer function, we find some x new here in the middle. We can reach. And this near function is saying, starting from x new as the center, we want to draw a circle with the radius of this, and so we want to draw a circle that is like this, and the radius is mean between eta and this log cardinality of V over cardinality of V. So eta is the limit for when you want to reach from x nearest to x rand. There is a limit eta, so you cannot go beyond the eta. That's some constraint we have, and this one is saying something like, so if there is only one component in V, then its cardinality of V is 1, and the log 1 is 0. So at 1 it's 0, and when it's at 2, so the function looks like this. So at 1 it's 0, and when it's larger, when the cardinality of V is larger, then the function becomes larger, and when the cardinality of V is too large, it becomes smaller. So so this is searching over this area and find and put all the points inside this area into this set x near. Yeah. So so we want to do something like V x new union x new, and x min, we just define a few new variable, x min, which is x nearest, and we have c min, that is cost x nearest, cost of x nearest. So if you cannot see this, you can always go online and check the next slide. So, but I'm writing this because I want to explain this to you like step by step. Line x nearest, x new. So here we define a few things like x min is x near. We assign x nearest to x min, and we assign cost of x nearest. That is the cost from the starting point to x nearest, plus the cost between x nearest and x new. So this is our minimum cost right now. And so now we want to do the real thing for each x near in x near set. We want to do so now we are checking all the points in this circle, and maybe I need another. So can I use another one? So if collision free x near x new cost and the cost x near plus cost of line x near x new is smaller than C min. So this is saying if from x near, which is different from x nearest, so x near is some point in the circle. So if x near does not have some collision between x near and the x new, and the cost of x near plus the cost between x near and the x new is smaller than C min. And what is C min? C min is here. The cost of x nearest plus cost of x nearest to x new. So why x near can be better than x nearest? Because x nearest is the nearest neighbor of x rand, and here x near is within the circle of x new. So we are now finding something to x new, and if this constraint holds, we do x min is actually x near instead of x nearest, and we do C min is actually this thing. Yeah. So here is something like we update the minimum state and the minimum cost if there is some x near point that is even better than the x nearest neighbor. Yes. So after doing this, we have the indentation. I think there is something like this. Like there is a for loop for each point in x near, and we do this. And out of this for loop, we have E is updated with the new thing we have, that is x min, x new. Yeah, and so we want to do the rewire. Next, we want to do the rewiring of trees. So for each x near in x near, we want to do. So again, we make a for loop in the circle of with the center of x new, and we check every point. If there is no collision free between x new to x near, and cost of x new plus cost of line x new x near, x near, sorry, is smaller than cost of x near. So this is saying if starting from x new to x near some point in the big x near set, the cost start from some starting state to x new, and x new to x near is smaller than the cost of the original path to x near. Then we want to update something. What do we want to update? We want to find the parent, x parent, which is p. Let's just do p x near. So p x near is finding its parent, and we want to remove this parent because it is not it is worse than x new. So we want x new to be its new parent or its new connection. So x parent. So this is removing x parent to x near. And we want to add x new and x near. Yeah, so this is the full algorithm, I think. I think with this algorithm, we can, let me show the printed version. Yeah, so so with this algorithm, we can always find a shorter path than the original RRT, because whenever you find the cost is smaller than the current loss, then the current cost, you just change the path because you remove the parent and you use x new as its new parent. So this is also asymptotically optimal, and the main idea here is swap the new point in as parent for nearby vertices who can be reached along shorter paths through new point than through their original points. And we can see some trajectory, like the upper row is RRT and the lower row is RRT star. So
just draw out what RRT does. You sketch out it's on the board with dots and circles. This is what's happening.
I see. So so we have some x new and we have that circle, and we check every point in this circle, and if where is the if it fulfills this constraint, then we just go from this point to x new instead of some original path to x new. Yeah, and we do the reverse thing for x near. If x near is closest to x near, then we do we remove some original path to x near and add the x new to the set. Yes, yeah. So I think we haven't finished, but we finished the main part. So after RRT star, there is LQR trees, but yes, so I will leave that to Pieter for next lecture, and thank you for listening.